All right. Hello, everybody. Happy Valentine's Day or Singles Awareness Day, depending on what you need. Hope it's a happy day regardless. Find a way to either binge on chocolate or something. And also, as you probably know, the mask mandate has become optional now. I'm just going to take a moment to comment on that because I feel like it's hard to think about it clearly when you have a strong opinion one way or the other. And so I think maybe I have a couple things that you might find useful, because for the pandemic as a whole and as it relates to kind of public health, how do we intervene, especially considering kind of developing countries? There's a lot of sticky situations, right? On the one hand, it's kind of not nice to tell people what they can wear, what they must wear. That's sort of an infringement on human liberties, right? On the other hand, it's a deadly disease spreading is important to try to control, right? So my personal opinion, and I'll share it from that perspective, since it's probably different than what you might hear from most people, is that it was probably a great thing to be taking action as quick as we could, including masks and travel restrictions and all that. However, I think that society had a really hard time keeping up with knowledge, because as soon as we understood who was really vulnerable, we could have adapted our approach, right? We knew young people, like most everybody here, barring certain medical conditions, were very safe. Pneumonia is not great, and this was a virus that was spreading really rapidly that caused pneumonia. And our bodies hadn't seen it before, so there was a lot of potential for a severe pneumonia response, right? So that's important. Pneumonia is something to be taken seriously pretty much regardless of your age. But we did know relatively early that young people were not at much risk. So like chickenpox, if these days, or when I was growing up, you wanted to expose people to chickenpox when they were kids so they could develop immunity, right? So that difference between kind of age groups should have or could have informed how we dealt with schooling, for example. And it would have been good to consider the costs of kids not being able to see each other's faces, not be able to be present with each other in school. Those are actually pretty big costs if you think about psychological and other things. So as soon as we had more information, it would have been good to adapt, perhaps been extra protective of nursing home situations, things of that nature, extra protective of public spaces where people had to go. You have to go to the doctor. That would be a place to take extra special care, and I think a lot of cases that was true. But in a college situation, if you're voluntarily here, paying to learn, maybe that's a different case, right? Maybe special care to allow people to attend remotely if they needed to or wanted to, because I don't want to know your medical reasons. You may have a medical reason yourself to avoid it at all costs, especially when we were dealing with bad pneumonia. Even today, you might have a lot of concerns, and that's totally legit. Or maybe you live with somebody, or one of your family members is super vulnerable. I had to take very special care when I went to see my younger brother. He suffered a traumatic brain injury over 10 years ago, and he's still kind of compromised physically and all that. So when I went to see him Thanksgiving of last year, not this past one, the one before, I had to be very careful. Kind of isolated myself as best I could for about 2 weeks, and my wife and I both. And then we felt like that was okay to go see him. So everybody has their own situation, right? So the best I can say for today, don't question whether or not somebody's wearing a mask, because society has to shift from a public decision to a individual risk decision. And so public arenas, something like a voluntary classroom, I'm streaming in case if you did have a case, you could tell me like, hey, I'm going to go visit my grandparents, and I just really don't want to be sick at all to see them. Just join on Twitch for a couple weeks. I'm okay with that, right? So that kind of option is what I see as a good approach, so that you can start managing it as an individual choice rather than like a choice that all of the public has to make. it's tricky. I don't envy any of the decision makers, because that shift from a public response to individual risk management is not an easy transition, right? So that thought there of it becoming an individual risk management decision, I think, is really important, and that's, I think, what a lot of society has been struggling with. How can we have it as an individual response versus while also considering public needs, and kind of in the public sense. So anyway, if you do feel like you are at risk, definitely get the high quality N95 type masks. Especially wear them if you are around somebody who's vulnerable, and that's your concern, right? I think we can all expect to get the Omicron variant at this point, and thankfully the data is very positive on that it's providing a lot of immunity, and it's not causing pneumonia nearly as often. It's much more of an upper bronchial tract type of system. So anyway, happy to see all your faces, and I hope that was somewhat helpful. I think it's always a good idea to be respectful of other people. We don't know their medical situation. We don't necessarily want to know each other's medical situations, and just have some compassion for wherever somebody's at with this dynamic. Okay, off my soapbox and on to explaining a little more about coagulation, unless anybody has any thoughts or questions, comments on that. Okay, so last time I was talking, I mentioned a couple things about coagulation. Wanted to kind of give them a little bit more discussion today. So I think our syllabus says we're moving on to granular filtration. We'll hold off on that till next time. So today I wanted to make a couple notes about particle stability. How do we understand it further from what we did last time, and then also talk about using organic polymers as destabilizing agents. So a bit of that, and we'll wrap up at the end of class with a kind of a discussion on using the Moringa oleifera seeds, kind of an extract for kind of a sustainable, natural sourced coagulant. Okay, so particle charges. Why do random particles floating in our water almost always have a negative charge? Well, there's a couple reasons. If it's something like a clay particle, sediment kind of stuff, some sort of mineral, one thing that often happens is you have some mineral structure, and this might look something like this, where you've got a repeated structure unit where you have maybe silica and oxygens, so a silicate substance. Then you can have some sort of substitution. In this case, it's showing a magnesium, so that's a 2+, whereas the surrounding structure, each of these oxygens is kind of a negative influence. The net balance would be that they would charge balance, right? But if you have that substitution, whereas Si over here, silica, was essentially serving as a 4+, its oxidation state, if you substitute an ion that way in the mineral, which does happen, just randomly, naturally, then you end up with more negatives than positives. And so you have a slight negative surface charge if you've got some of these substitutions going on. So that's one common way for kind of inorganic particles, clays, minerals, that kind of thing. And on the other hand, we have more organic materials. So maybe some soil particles that are, rather than mineral, they're kind of organic. They came from some maybe leaves and things that dissolved, and then bacteria munching on them, just random organics. You have some sort of particle, and it's made up of who knows what organic chemistry. And what you can define or notice here is at the ends, wherever it's kind of interacting with water, you'll have different little functional groups there. And a lot of times you can identify these surface sites that will say the surface is this S, the 3 bars. We can think of it like a particle coated with these organics. So you'll have these OH2, that can be a positive. You can have just an OH, or you can take that hydrogen off for a negative. This is kind of just acid-base chemistry, right? That proton, you can protonate it, get the positive charge, you can deprotonate it, and get a negative charge. So it's kind of acid-base chemistry on these random hydroxyl sites on the surface. And this applies to carboxylic groups, to amine groups, several other types of functional groups that are just going to be randomly a part of these particles. Maybe you can design a specific bead or something that's coated. I've seen kind of in scientific studies, it's pretty common to take like a polystyrene beads and then coat it with amines, and then you can attach things or manipulate that little microbead in water for whatever purpose you want, and it's going to act like a nice, neat little particle, and you can cause it to have a negative charge if you have the pH kind of in a normal or basic regime, or maybe a positive charge if you drop it low enough. So each of these reactions, they typically will have that pKa or that Ka value, that equilibrium constant for how likely it is to add or subtract that hydrogen. And it just turns out that most organics, if you have something near a neutral pH, you're going to have a lot of negative charges. You'll have a lot of this O minus, or maybe there's some other COOH, lose the H, and then you have a minus. You know, you get the picture there. A lot of times in kind of natural systems, or we could say near neutral pH, there are enough of these that tend to have a negative charge that it's slightly balanced towards the negative. And you'll have a net negative charge. Okay, so it's acid-base chemistry that you've seen before. That's just applied to this really complicated system. You don't really know what all's happening there, but you know that there's enough of these types of groups where it's going to happen, and you can then observe with some other methods and check, and sure enough, most particles are going to be negatively charged for these reasons. Maybe if you have something strictly coated with amine groups and very carefully controlled, maybe that'll be positive charge at a neutral pH. But that type of a situation, or actually, and this is some of our antibiotic chemicals are actually intentionally positively charged to disrupt bacteria. You can do it, but it's usually a very intentional or very specific case. Okay, we talked a little bit last time about van der Waals, and I had to realized I had a little bit more materials for you here just to kind of demonstrate. So these are the forces. If you do get particles close enough to each other, they attract based on these forces. You just have to get down something like 5 nanometers apart or something, whereas normally the electric fields kind of repel each other up to maybe 10, 15 nanometers. If you get them close enough, these van der Waals forces become stronger than those repulsive forces. So these are caused essentially by what we can call electrical dipoles, distortions in kind of the electric, not the electric field from the charge, but the actual electron clouds spinning around the molecules and atoms. Those can create some attractive forces once they start interacting with their neighbor ones. So there's a few things like that, and then hydrogen bonding is kind of a similar property. That's how water interacts. Water doesn't bond to other water molecules, but the hydrogens face each other. If you have hydrogen, oxygen, hydrogen, it's one water molecule, then another one over here. These tend to interact and are a little bit sticky with each other, right? So that's one of these van der Waals forces. And you get things like this gecko that can climb upside down on a very slick surface, or these little water skeeter bugs, whatever they're called, that use surface tension essentially from the van der Waals interactions, or a kind of a repulsive thing there. That's the surface tension of the water. The reason water sticks together and doesn't let the little leg fall through, that would be van der Waals. That's hydrogen bonding. So we've got surface tension there associated with these, whereas the little bug has something that's acting repulsively to all that. So kind of a similar process. Okay, so then a little bit extra about precipitation reactions. We talked about it, I mentioned it, but really if we want to know how and why it works in water, then we have to think back onto anytime we've done precipitation in chemistry. So all sorts of metals we could use, and specifically we'll often use precipitation reactions. We can remove metals because we can create lots of solids, solid metal precipitates. We can reduce hardness with precipitation, and primarily what we're looking at is flocculation for our class, but some of the benefits you might get is potential removal of, let's say, arsenic. If you do or design a flocculation process correctly, maybe you can actually get rid of some of the arsenic while you're at it. Not just particles, but if you're doing the precipitation side of things. Maybe you could change hardness. That's probably not a big concern for kind of point of use developing cases. There's usually a lot more acid-based chemistry, a lot more chemical resources there, and hardness is kind of an aesthetic that's really mostly important for avoiding scaling on your plumbing, and in a point of use case, you're going to have a whole lot of plumbing typically. Maybe there's some issues with soap suds forming, but again, you just kind of get around that with more soap, and that could be fine. Okay, so then that leaves us with flocculation. We already talked about alum and ferric chloride, and kind of an FeSO4 ferric sulfate. So how does it work? Precipitation. There's a couple ways. Most of the time we can think about it as we have some sort of a solute, so that would just be our dissolved molecules. Those will end up forming little clusters, which then we could call, that's becoming some sort of a nuclei, and actually I think should draw that like this. We form little clusters, and then we end up, those clusters might start sticking together. We get these little nuclei events where we have kind of a cohesive structure that then little parts start adding onto. So then that ends up building a larger structure. And in the case of something that's crystalline in nature, we'll have a very ordered structure that might look like this little box, where you just have little components adding to it in different spots. So that would be what we would call homogeneous or primary precipitation. That would often be starting from scratch like that in terms of like a single particle, and then it becomes a larger particle, and then a larger particle, just starting like that. Whereas we could also consider a case where we have precipitation reactions occurring in what we call a heterogeneous or secondary nucleation type of event. And this is where you have something added to the system to intentionally allow more sites for precipitation to begin. So you may have seen this or heard of this nucleation process in a couple different systems. Essentially, in a sedimentation basin or a reaction coagulation situation, we might add a ballast. So that would typically be sand or something like it. It's going to be really easy to remove that sand from the water with sedimentation. It's going to come out anyway. But while you're doing the coagulation, you can add some of that sand, and then particles can start forming around the sand, so it's kind of a seed. So we use some sand or something like it to seed the precipitation. So it gives the solutes something to start solidifying around. And I mentioned you may have kind of heard of that type of dynamic in a couple places, and there's a couple of interesting ones that come to my mind. If you think about cloud formation, a lot of times you can seed cloud formation if you have maybe soot or some sort of particle released into the air that's the right size. Volcanic activity can do this, and you can essentially provide a parcel of air with enough particles that the humidity in that air can start forming water droplets, right? So there's a lot of water droplets involved there, and they can, or a lot of water there, and until they had something to start forming a droplet around, it just wasn't energetically efficient to do so. So there's some thermodynamics there in terms of kind of the surface tension stuff and all of that. So that's one case. Another case in a water system would be if you ever do the supersaturation case, where you have a supersaturated jar of sugar in water, and then you add like a stick or a string into the water, and crystals start forming on that object, because now they have something to start attaching to. So that would be a nucleation example. So the supersaturated sugar solution. And perhaps the most interesting, that you should not try at home, is that apparently if you take very pure water in a very clean container that's microwavable, and you microwave it for a long time without any motion, any jostling, any stirring, so you have to remove the little rotating plate, then you can get water at an elevated temperature that can be a lot higher than boiling point. And the reason you should never try this at home is because if you do that successfully, and then anything disturbs that water, it's immediately going to boil. And it's going to be probably explosive depending on how much higher temperature you have it than 100 degrees Celsius, right? Because it's going to be way overboard. And so then if you bump the microwave, you open it not carefully enough, then you have an explosion, and chances are you use something like glass maybe to do this in, because you can melt the plastic if you do that to plastic. Then that's, not only are you potentially having exploding ultra hot water, steam happening in your face, but also glass shards. So don't try that at home, but apparently it's a thing. I guess it's superheating water is apparently possible. And it's kind of the same idea, where if you don't have something to allow the bubbles to start forming in solution, to go from liquid to gas, apparently you need some disruption or some surface site to allow that process to start moving forward. As soon as you form one bubble, that's probably going to catalyze all sorts of other bubbles. So again, don't try it at home. Okay, so then in practice, looks pretty gross if you're doing this precipitation type reaction. Here's a flocculation basin, or rather probably just going from coagulation into flocculation. So it's still pretty rapidly stirred here. If we're adding iron, aluminum, sulfate kind of stuff, it's going to look pretty messy, because iron in particular has kind of that color. I don't think aluminum sulfate, so alum, is any prettier. So it's going to look pretty nasty, but then, of course, the goal is at the end of the day to remove it, and it turns out iron and aluminum fairly safe to consume, even if there's a little bit left over. We're going to basically, in these precipitation reactions, we're going to be manipulating the solubility chemistry. So it's going to be equilibrium chemistry you've learned about before, where we have some solubility product that's going to typically be something like our Al3 plus and let's say 3OH minus is in equilibrium with a solid aluminum hydroxide form. Something like that. So then you recognize if we add base, that should push the reaction to the right. Or if we have sufficient amounts of that and we're adding aluminum, the same thing would happen. So essentially when we're doing these systems, we want to be cognizant of that, and then also cognizant of the value here that's kind of really telling us how soluble it is, how much is it going to be in the solid form versus the dissolved forms. And it turns out that if we take a look at solubility products table, lots of data here, all sorts of different solids we might think about. That one in particular, the aluminum hydroxide there, I guess I wrote it backwards, maybe probably be, if we're talking about solubility products, we're going from solid as the reactant to dissolving into the products, but you get the picture. So if we define it that way, then this the number, the solubility product here for this form is a very, very small number. So that times 10 to the minus 32. So a very, very small amount of that is going to be in the dissolved form. So I wrote it kind of incorrectly here, but essentially, well, I'll just fix it. So I'm just gonna rewrite it so that we have it here properly. And if we write it this way, then it will make a little more sense with the solubility equation here. That's really what I wanted to highlight. So if we write it this way, then we take this KSP and relate it to that. The way it relates is we have Al3 plus times OH minus. This is going to be to the cubed power because we have 3 of them. And that's going to be divided by the solid, which is, we treat it as 1. We just treat solids as unity for, and liquids, the concentration of a solid or the concentration of a liquid, we treat it as 1 for these types of reactions. So anyway, that means that if the product of aluminum times hydroxide is very, very small, that means a very, very small portion of it is in that form. So when we take a look and say that's something like 10 to the minus 32, we know that very, very small amount of this is actually in this form. Most of it is then in the solid form. So that's what we learned from this table, seeing that it's so small, right? So that's the point, and that's why this is going to work so well, so long as we have our chemistry such that there's plenty of base to be consumed, which is why we typically are going to add some sort of alkaline agent alongside. If we were to look at the solubility product of aluminum sulfate, so this would be Al2SO4 3, and we were looking to take a look at that, that KSP would be a relative, very large. So 10 to the, I don't know, 10th, I'm making up a number here, but it would be definitely a high number because it dissolves very readily. So that's the way we can think about it. And typically, we're not adding so much that we have any solids remaining, it's just all going to dissolve. And then it's a forward reaction because it's so soluble. So just a couple notes on solubility there. Probably all heard that before. And I really just want to highlight the aluminum and iron hydroxy solids here. It notes that both of these are amorphous. So they are both, when they form solids, they're not like a crystal structure. It's kind of what that means. They're not very ordered. They're just loose, random aggregations of particles. I think we talked a little bit about calcium sulfate or gypsum last time. We can see that here. It's definitely not nearly as insoluble as those cases, but it's one of the more soluble of these solids, but we might be able to form that as a precipitate as well. Okay. You can see several other, some heavy metals and things here that might precipitate under certain situations, maybe relevant in some other cases, but really what I wanted to highlight was these two, times 10 to the minus 32, times 10 to the minus 39. Definitely highly insoluble. So we can get at those numbers with thermodynamics, not really the focus of the class. I just wanted to note those solubility product numbers are coming from kind of chemistry and maybe some of the more theoretical or empirical chemistry here, where we can get this Gibbs free energy for that reaction and look at the enthalpy, all that, to come up with these solubility products, and they are temperature dependent. Now, most of the time for our case, it doesn't really matter too much what the temperature is. They're just so insoluble that anything we might be working with is not really going to matter. But that's where these KSP values are coming from a function of that, the Gibbs free energy, the temperature, and all that. On the other hand, we can look at particle precipitation. So taking the particles and forming larger and larger particles around that. There is some thermodynamics there as well, I mentioned earlier, to do with the nucleation. So having maybe if you think about the surface tension broken in the superheated water example, if you break the surface tension, maybe that's enough to allow the formation of gas bubbles much more easily. Something like that. If you have some sort of external disturbance, sometimes that reduces the potential energy for some action or some process to happen. So if we take a look at this free energy change, that's kind of the amount of energy required for something to happen, this nucleation or the precipitation reaction to happen. And we look at that as a function of how big our particle is. We can actually see something interesting. So if we take a look at this line here, as soon as we're below that line, that's zero energy. If we go negative, it's a favorable reaction. And I actually don't remember what this figure is talking about with the SS1 versus 10, all that. It's something to do with this flocculation process here. But the point is, if we manipulate the solution, maybe providing the right ballast or something, as soon as we get that nucleus large enough, or maybe seed it with something large enough, then we start getting negative energies, and then we'll have precipitation. So maybe this is concentration, maybe this is some other aspect of the particles or what we're dealing with, but as soon as we get it to the right point, at some size, it becomes favorable, and all of a sudden we start having precipitation occur. It's kind of what this graph is showing. Likewise, if we look at the number of particles, and this is on the right here, we have a seeded versus unseeded case. And what we're looking at in that figure is how many particles are in solution at different sizes. So it's a particle diameter on the bottom, and this is a particle size distribution function, just meaning number of particles in every, it's a number of concentration of particles. So if we take a look and we add, let's say, sand, well, we added a bunch of particles, so we have a whole lot of particles here. But the other thing that's happening is it's causing this coagulation, so we're reducing the amount of particles that are small. So fewer small particles remaining in solution, lots and lots of these larger particles, but it's okay that we have more particles so long as we shifted them larger, because then sedimentation can take care of them. Right? So that's the thought, right? We're doing coagulation, then sedimentation. So if we compare that to never adding any seed in the first place, we just have the particle size distribution look like that, where we have a lot of particles that are really small. So what we want to do is decrease the number of small particles. That dip there is really what we're after, because we can't settle those ones anyway. So those are the ones we want to decrease. We want to stick them together into these larger particles, and on top of the ballast seed particles that we're adding on purpose, because we'll be able to settle all of those no problem. And if we take a look, that cutoff in this example is 10 micrometers. And that's the example we used the other day, and we said, okay, 1 meter, we could probably get that, a particle, maybe a clay particle that's 10 micrometers diameter. We can probably get that in, 200 minutes or something, right? It was relatively reasonable amount of time. We may be able to expect that for a point of use process. Okay, so then the other aspect of precipitation reactions is really kind of the geochemistry, what kind of minerals can form, what kinds are going to form precipitates, and how much of some random element, or whether it's aluminum or iron, or in this graph is showing copper, at what point are we going to start forming the solids, and then we'll have lower amounts of the copper in solution. So in this case, dissolve some sort of a copper form, and the total amount of copper is pretty high right here. But at some point, we end up starting to form solid precipitates, and the total amount of copper left decreases to a minimum at pH 9 point something. So based on the pH that we're dealing with, there's a function there, and we can see that different aspects, different forms of this copper may be forming in different places or may be dominant. So essentially what we're looking at is optimizing our solution based on the precipitation we want to have happen. We're probably not going to take this elaborate of an approach for doing coagulation in a point of use case, but this kind of shows us why maybe if we were going to design a long-term solution to a local water supply, we actually do care about the chemistry of that water. If it's groundwater, we want to know what's the pH coming out of it typically, how alkaline is it, or how much buffering capacity. So how hard would it be to change the pH? Because that would go into designing our coagulation dosing. Of course, we can do jar testing kind of stuff, but that's what would be better is to have a good idea up front of like, okay, well, what kind of coagulant do we need in the first place based on that chemistry? Okay, so from there, we have a bit more about the coagulation itself. I want to talk about sedimentation, coming back a little bit. We talked a couple lectures ago about discrete particle settling, just one particle falling. We could talk about sedimentation with flocculation occurring, so we start having these aggregates that are forming during that process and starting to interact as this aggregate settles. So that would be important. That would be kind of the second one. So this would be 1, 2. Then we have what we would call hindered settling. Once we have a lot of this stuff going on, especially if we have like a precipitation reaction, or maybe we're dealing with some particularly dirty water, and at some point, like towards the bottom, we get so many particles. The particles themselves are preventing other particles from settling as much. So that would be, we might find some zone where we have that effect starting to happen. And actually, I'm sorry, that's compression. So if it's preventing each other from sedimenting, that would be compression, so that would be 4. And the zone settling is a similar case, but essentially what happens is we end up with kind of a blanket forming where all these particles that are falling really start collecting into a mass and are then sweeping through the chamber or the water column and catching particles and like catching them all together at once and settling faster than maybe the other particles would have been settling. So we end up getting this zone where it's really highly concentrated and they're sticking together and they're falling and they're all grabbing each other that way. So it's like a net almost falling through the solution. So this would be the number 3. So not a whole lot to talk about there aside from maybe if we think about a point of use case, if we're adding some coagulant and a ballast, maybe we're going to end up with a 3 into 4 situation, or maybe just 2. We're not going to be doing these calculations all the time in terms of like, okay, what's our particle size? How dense is it? All that. We're not really going to take that approach. So we're not actually going to take that discrete particle, maybe at the start, just to think to ourselves, okay, what's an approximate time frame if we know something, or have some estimate about the particles, maybe something about the soil in the area. But ultimately, we'll probably do some sort of a test. If you really need to know the dynamics of the system, you can do some empirical tests. If you take a kind of a column of water, maybe like a large PVC pipe, fill it with water, and then have a bunch of little spigots to check from. So you do your process, you put the water in it with all these particles destabilized, and then you let it settle, and you check maybe every 15 minutes from each of those, what's the turbidity? How much particles are in there? So then you can kind of talk about how quickly are you going to achieve your particle removal goals, how much particles are there, what's the particle concentration at a specific spot at a specific time, and with all that data you can make kind of a little map here to say, okay, if we are looking for 70% removal, we saw that the turbidity had decreased by 70% across this line, where at 2 hours 70% of the particles had been removed in the upper half meter of the thing. So you can kind of make a chart and kind of decide, okay, well, if we just needed 30% removal, we can get that in 40 minutes. If we needed 100% removal, we need to leave it for, this many hours. That can be a handy way to look at it from an empirical sense, and you could model that speed based on kind of how high, basically the velocity is going to be, how quickly the particles are moving through the water, right? It's the change in height versus the change in time. So pretty simple there, but as you can imagine, with a real water sample with random stuff, you're not going to be able to really model it mathematically. You're going to have to do something like this, or just maybe a simple jar test based on what you need. Okay, so that brings us to polymer coagulants, and here's where I think one of the kind of the neat innovations in sedimentation. I mean, it's not a whole lot innovative about gravity, when you first think about it, but the use of naturally occurring substances is a pretty great idea. So essentially the polymer bridging technique. This is a tool we can use to destabilize particles by essentially adding some squiggly little polymer, and the idea is that it's going to have probably a positive charge here, or something that's at least likely going to interact with the surface and get the van der Waals sticky stuff happening. So you have some way of it sticking. Maybe that means that it's kind of negatively charged in the middle, positively charged at a couple ends, or in some other way likely to interact based on the chemistry. So what we want is for it to form these interparticle bridges. Got a nice little drawing here. We've got to add a bunch of those. You get these particles, and then they sort of entrap into a mesh aggregate sort of a thing. And when that encounters other particles, those stick as well. There's a couple of potential problems. If you actually don't have enough particles in there in the first place, well, maybe your coagulant stuff, your polymers end up just sticking to the same particle and not really finding other targets, and you didn't really do much but add some gooey stuff into the water. Hopefully that would settle out, but at least it could be ineffective in some cases. The other thing you want to avoid is overdosing, because if you end up sticking a whole bunch of these polymers and they all attach onto one particle, and then you have the same thing happen on another one, suddenly it might be the case that you now have positively charged particles that are effectively these urchin-like particles that are now repelling each other, right? So we wouldn't want that situation either. So there are some cases where this approach can fail. So like with the other coagulation dosing situations, probably a good idea to test it out and do some metrics in the field to see how well it's working. Okay, so then let's talk about the Moringa oleifera. It's a type of tree. That's the scientific name of it. It probably has common names, kind of depending on where you go. As I understand it, it's present in most tropical regions, nearly all continents. So this is a very common tree, very commonly found. I think there may be some other potential herbal or medicinal uses for the leaves and things, but for sure the seeds are harvestable, and then you can essentially grind them up, get a bit of an extract, and then use that as a coagulant, because it turns out these tend to be positively charged, have a lot of positively charged molecules that essentially act like those interparticle bridges. And so it's kind of a naturally occurring substance with these ionic polymers or ionic molecules that are large enough to do this bridging effect. My postdoctoral advisor, who I worked with in Michigan for about a year, He's been doing some work on this in particular to kind of weigh out the pros and the cons. And so this morning I was looking and I was like, I wonder if I could get some of the information from his research to share with you. And then like I found that, come back to this in a second. I found that just a few days ago, he had an article published exactly kind of what I was looking for. So we'll talk about this in a few minutes, but essentially he's like taking these moringa-derived coagulants for water treatment. So taking a look at the floc structure, the residual organics left, you wouldn't want to accidentally poison the water with some seed extract, right? So what's left in the water, and kind of just analyzing the performance trade-offs here. So we'll take a look at that. It's hot off the press, kind of fun. But before that, our book has a couple of informative pieces here I'd like to work through, and an example problem just to kind of get ourselves thinking about practically, if you wanted to do this as a sustainable source, how many trees do you need? How much land area is that going to require? Like how much resources do you really need to devote to it if you're going to plan on using this 24/7 for a kind of a sustainable goal here? Okay, so this is from box 18.2, using these seeds to treat water. So this is just a little instructional thing, and we see in table 18A some typical dosing required based on the amount of turbidity, so kind of the amount of particles in the water. So first, we allow the seeds to mature, dry naturally to a brown color while still on the tree. So you let this tree grow, do its thing, form the seeds, and you don't harvest them early, you let them mature essentially. Then you take them, remove the seeds, and shell them, you crush them, and then sieve them with some sort of a mesh, 0.8 millimeters is what it's recommending. Mortar and pestle, you crush the seeds, right? Seeds and the powder can be stored dry. Then you mix with clean water to form a paste. So 2 grams of the seed stuff treats 20 liters of water. As a rule of thumb, the powder from 1 seed kernel treats about 1 liter of very turbid water, or 2 liters of something that's kind of medium turbidity. The paste should be freshly prepared for every treatment. So that means you need to do the crushing before use. So if you were to crush all of this and store it for a long time, it's probably not the best idea. The molecules may decay or kind of go bad in some way. I think that's kind of what it's talking about here. Okay, so then we can see, these typical ranges. You're going to need doses that range from 10 milligrams per liter to 200 milligrams per liter, depending on how dirty your water is. So that's not a huge concentration. So that the highest there, that's 0.2 grams per liter. You certainly notice it if you're adding that much in, but it's, that would be probably about like 1 teaspoon in a liter of water at most. Okay, so that's not a whole lot. It depends on the density of it and all that, but it shouldn't be too much. 200 milligrams is not a large amount of stuff. Okay, so then number 5, dilute the paste in a cup of water in a sealed bottle. Shake the solution for 5 minutes. So that's going to have to shake it for 5 minutes. If I sit here shaking for 5 minutes, I'm going to wear my my wrist out, my arm out, whatever. So you can imagine it's going to be a little bit of a pain, but certainly possible. And maybe it doesn't have to be vigorous. Maybe just a little shake here and there might be okay. And that's to do 2 things. One would be to release the chemicals, but also really disperse it well through the system, right? That would be in a full-scale treatment plant. We'd often have a coagulant mixing spot where it's essentially a very small chamber with a big pump. It's just providing rapid mixing and then sending it along into the flocculation chamber. So that's kind of what happens there. Then you filter it with a fine mesh. You can have kind of particles from the seed crushed up. You don't want all those particles in there that are just going to float around or whatever. So you send it through a fine mesh cloth type of situation, and then it's essentially ready. So that's preparing Okay, so that's what's happening. They're preparing, like, if I were to make some liquid, then I'm going to add to a larger container to do the coagulation. So then this next few steps, that's for then pouring that into a larger container to treat for drinking water. So pour the solution into the container for water to be treated, stir rapidly for 2 minutes, then slowly stir for 10 to 15 minutes. Okay, so the vigorous shaking, that's just to break apart the seed stuff. And then you let that sit for 1 to 2 hours, do not disturb. This allows the sedimentation to happen. So, and you notice here it's 1 to 2 hours now that we've done this coagulation. We no longer need that 24-hour kind of a deal. Hopefully we're destabilizing a lot of the pathogens along with the particles, right? So that's going to provide that aspect, and we would then assume that some of those eggs that we were letting decay after 24 or 48 hours, those would hopefully be caught in this, so we're kind of taking a different strategy. So once it's settled, at the bottom, we want to carefully pour off the non-particles, the cleaner water, and then we can use that. Okay, so as an example, why don't you go ahead and do this? I'll set up a Kahoot, again, just to kind of get your attendance and see who can get it right. And so the problem is here, to calculate the required land area to treat water with a turbidity of 15 NTU, and I'll come back and give you that dosing suggestion that they gave. With a process flow rate of 10 cubic meters per hour that operates 8 hours per day for 1 year. Okay, this is going to be some unit conversions. Let me flip back for a moment. For 150 NTU, that was right kind of at the 100, somewhere between 150. We're going to call that 75. So we're going to say the dose range is 75 milligrams per liter. And we'll go with that. The solution here might have used some other number, and I'll adapt if we need. But go ahead and work that problem out. Take a few minutes. I'm going to set up a Kahoot while you do that. Okay, and actually the book solution is using 100 milligrams per liter, so assuming you're not too far into it yet, let's use that instead. Okay, I think that there's some more information you're going to need now that I'm thinking about it. Hang on. So I think the book previously gives some information about kind of land area usage. So let me find that for you now that I'm thinking about it.
How much milligrams like are produced per tree, I guess.
Yeah.
And then like how much area a tree takes up.
Okay, so let's do this. So the book just before that spot, let's say, gave some information. Okay, when the seeds are used, let's see, the tree yields 3 kilograms of seed kernels per year, and you need a spacing of 3 meters. Yeah, so I think that gives all the information needed. I apologize about that. Okay, so and then
With a spacing of 3 meters, like radius? Or just, you know?
Yeah, I would do it probably linear, like you could do a grid kind of thing. You'd probably do like 3 square meters per tree or something. I think makes sense. And actually, as I'm looking through this, it does say, it does give you some metric tons per hectare. So give your answer in hectares, okay? So you use that rather than the 3 meter calculation. And you probably want to design it. I mean, actually, I'll let you decide on what to do with 3 to 5 there, because that'll be a good thought exercise for you. guys about ready? So by the way, this is a pretty good example of what I might give you on an exam to discuss, right? So I can give you something like this that's not, you didn't have to memorize any equations to get this, so long as I actually gave you the right information, right? It's a word problem you can handle. But then to be thinking critically about it, or maybe to make a decision about what to do with the range here of 3 to 5, what makes most sense for a design criteria in a developing country, some critical thought on that, and my thinking here, I'll explain in just a moment. So we'll see what you thought. So let's do a Kahoot. And hopefully, there you go. Okay. So a lot of the intent here is kind of to be, so use your 8-9 number, please, and we'll get your participation that way. But yeah, for the final exam and just for the class in general, my thought is to equip ourselves to really think about the different dynamics that would be at play for these sustainable approaches to water treatment, essentially. Anybody need a moment longer to get in? Okay. Just give me a thumbs up when you're good. If you need more time. All right. Here we go. So basically, I just put in like, okay, is the answer less than this amount or less than this amount? Just answer the one that is true, that is closest to your value. And if you've calculated, let's say 8 hectares, then that orange one would be closest to your value and be true according to your calculation. Okay, so it looks like most of you got that right, or approximately right at least. And just because you guys like to see who got first, if you recognize your 8-9 number, it is whoever this is answered the fastest and the correct one. So congrats. Okay, so let's go back to the problem then. And we can just look at it here actually. So essentially what they're saying is we take this land area calculation. They used the the production of 3 metric tons per hectare. So that's essentially the lowest amount available, right? So in the problem it said, or in the context, it said 3 to 5 metric tons of seeds per hectare per year. So that's kind of the more conservative approach, in the sense that if you base your system on a high productive yield year, what happens when you have a bad year, right? So you'd want to design it in a way where you can avoid having an issue there. So that makes sense to me. So that decision there for that component seems right. So otherwise, they're saying, okay, 100 milligrams per liter for the dose. We need, the conversion here from milligrams to kilograms, because we were working in kilograms. We have a conversion for or the flow rate here, 10 cubic meters per hour, 1,000 liters per cubic meter, 8 hours per day operation, 365 days per year, and that gives us some mass of seeds that we need for the operation. And then we can take that, and we know that we get some amount of kilograms for every hectare, so 1 hectare provides 3 metric tons. So metric ton is 1,000 kilograms, and we can look at it from there. Okay, so then it summarizes and says approximately 1 hectare of land is required for these trees to provide that level of treatment, and 10 cubic meters per hour, so that gives us 80 cubic meters for an 8-hour session, so 80 cubic meters in a day. That's going to be a fair amount of water, so that's going to be a small community, I believe. Not just a couple of houses, but maybe a community of 50 houses or so, I would guess, maybe more than that. Okay, so that's a pretty good example. A little bit short on time, so what I'm going to do this. I'm going to say, take a look at this article. Let's read through it, kind of as homework for Wednesday. We'll do probably a small Kahoot quiz that I might take partially for credit, just to kind of give you some incentive. Like, you get most of the credit for actually being here and participating, or being online, and then maybe there'll be 20% of that. You could lose credit if you get the wrong answer. So take a look at this and specifically read about kind of the dynamics as they relate to what we talked about. Okay? So I'll have a couple questions on you for that for Wednesday. So I'll post that this afternoon. That'll be for Wednesday. And I'll see you Wednesday.